friends, in our last discussion on the types of radioactive decay, we have discussed about alpha, beta and gamma decay and what happens for the parent nucleus when each of the alpha particles, beta particles and gamma radiation is emitted from the parent nucleus. What happens to the atomic number and the mass number of the parent nucleus and the daughter nucleus. We have also seen how some amount of energy is also emitted during this process. Now we are going to go towards the mathematical derivation of this process, which is called as the law of radioactive decay. Basically speaking, in our earlier textbooks there was a definite statement indicating the law of radioactive decay, which said that the rate of radioactive disintegration. Now this rate means the number of radioactive nuclei disintegrating per unit time is directly proportional to the number of radioactive nuclei present at that time instant. But this type of statement is not at all given in the new textbooks. But still then, this can be taken as the basic line for the derivation of law of radioactive decay. Also, we have to see what every stepwise derivation means, because in the new textbooks it is given within a very short derivative form, but here we shall have to discuss step by step in details. Let us see the stepwise derivation for the law of radioactive decay. For that, let us understand that let N0 be the number of radioactive atoms at time t equal to 0. Next, let N be the number of radioactive atoms at time t equal to t. So these are the basic two things, N0 and N. Let a small fraction of this number of radioactive atoms, that is Dn, they will be disintegrating in a small fraction of time dt. That means we have dn by dt is the number of radioactive atoms disintegrating per unit time. Let us say this dn by dt is the number of radioactive atoms disintegrating per unit time. We can also call this dn by dt as the rate of radioactive disintegration. Now, according to the decay law, which I stated earlier, this rate of radioactive disintegration is directly proportional to the number of radioactive atoms disintegrating at that particular time instant. That means dn by dt is proportional to n. Together we can put this as dn by dt is equal to minus lambda into n, where lambda is the constant of proportionality and it is called as the decay constant. What is lambda called? Lambda is called as the decay constant and its unit is so many nuclei per unit time. This time may be in seconds, it may be in minutes, it may be in days, or it may be in years. Now let us proceed. Integrating the above equation, integration of dn by dt is equal to integration of minus lambda n, or we can say integration of dn by n within the limits n equal to 0 to n equal to n is equal to minus lambda dt. So the value gives us log to the base e of n is equal to minus lambda t plus c. Log to the base e of n is equal to minus lambda t plus c. In that equation, c here is the constant of integration. As our mathematical process goes on, we say we have to find out the value of this constant of integration. Then we say that at time t equal to t0, let n be equal to n0. This n equal to n0 means at 0 time n0 is the number of radioactive atoms. So putting in the earlier equation, we have log to the base e of n0 is equal to 0 plus c, thereby giving c is equal to log to the base e of n0. Substituting the value of c in the earlier equation, we have log to the base e of n is equal to minus lambda t plus log to the base e of n0. Now taking n0 on this side, we have log to the base e of n minus n0 is equal to minus lambda t. When we subtract any log, it is actually the division of two numbers. So log to the base e of n upon n0 is equal to minus lambda t. Now we have to eliminate this factor log to the base e, so convert it in this exponential form. So n upon n0 is equal to e raised to minus lambda t, where n is equal to n0 e raised to minus lambda t. Mathematically speaking, this equation with a negative sign of the decay constant indicates that this equation or the graph will be of an exponential nature. Now the negative sign in this equation or earlier of these equations where dn by n gives minus lambda t plus c and so on, the negative sign indicates that as time goes on increasing, the number of radioactive atoms goes on decreasing. So we have to specify every time the significance of the negative sign in the equation. Now let us look closely at the graph of this radioactive decay. Now this is a typical graph of the radioactive decay. This graph is also not given in our textbooks, but we have to explain it because we are discussing about the exponential form and we are calling it as an exponential decay. Now when a graph is drawn with time on the x-axis and number of radioactive unchanged nuclei on the y-axis, we say that as time proceeds, the number of radioactive atoms goes on decreasing with time. It never becomes abruptly zero, but it goes on decreasing exponentially with time. Let us see that at time t equal to t, the number of radioactive atoms is n, and after a time interval of dt, the number of radioactive atoms decreases by n minus dn. So if we go on plotting a graph of these values, we get this particular curve which is called as the decay curve. Remember the name, it is called as the decay curve, and the nature of this curve is exponential. Let us continue with our next derivation about the half-life of a radioactive material. Now as you see here, that the definition of half-life reads as the time taken for the number of a parent radioactive nuclei of a particular species to reduce to half of its value is called as a half-life period, and it is indicated by T half. Suppose there is 50 gram of uranium present, then by way of radioactive disintegration, this amount of uranium reduces to 25 gram. Then the time required for uranium to reduce from 50 gram to 25 gram is called as the half-life of that radioactive material. From our famous equation of radioactivity, we have n equal to n0 e raised to minus lambda t. Here at time t equal to t half, this t half is called as the half-life. Then n will be equal to n0 by 2. Also we substitute in this above equation, n0 by 2 is equal to n0 e raised to minus lambda t half, or 1 half is equal to e raised to minus lambda t. Then e equal to lambda t half, that is equal to 2. Every time we have to write it as t half. So lambda t half is equal to log to the base e of 2. That gives you 2.303 log to the base 10 of 2. That is 2.303 into 0.3010. Therefore, lambda t half is equal to 0.693, or we have the equation for half-life period as t half is equal to 0.693 upon lambda. The unit for half-life period may range from a few seconds or minutes or days or years together. The equation is the half-life of a radioactive species. Now in this derivation we have to understand, let the number of radioactive nuclei decaying between time t and t plus dt is given by lambda n0 e raised to minus lambda t dt. That was from our earlier equation of radioactive disintegration. So the lifetime of these nuclei is t, and the average lifetime tau of a nucleus is given by we have to perform this mathematical function tau is equal to 1 upon n0, and integrating it within the limit 0 to infinity, we have to integrate the remaining equation t lambda n0 e raised to minus lambda t dt. That will give us lambda integration of 0 to infinity t e raised to minus lambda t dt. Integrating we get tau is equal to 1 upon lambda, and the relation between the average half-life and the half-life period which we saw just now is given by t half is equal to tau log to the base of 2, that is log to the base e of 2, that is 0.693 times tau.